thank you everybody for coming today to the Flexible Funding 2002 Project Showcase with us here at the UK CCSRC. My name is Muir. I'm a researcher at the University of Manchester with the Tyndall Centre. I'm also an ECR researcher with the UK CCSRC. And today we're going to be showing you two very impactful, very good projects here from Nejat and Ali. We've just got some housekeeping rules that we have to look into today. So throughout the presentations, if you have any questions that you would like to ask them, could you please put that in the chat or wait until the end of the session to raise your hand and we can pick you out for any questions. And we'd kindly ask, while people are presenting, could you have your cameras and audio off just to make sure there's no disruptions there. So as we're just going to go straight into the first presentation here from Nejat, from the University of Bradford, we're looking to a great presentation on the sort of evaluation of the properties of different biomass woods for pellets in power generation. I'll just hand over to Nejat. Are you okay to screen share?
Good afternoon, everyone. Thank you, Muir, for the short introduction. This is Nejat Rahmanian. I'm an associate professor in chemical and petroleum engineering and the same time program leader for MSc course at the University of Bradford. I'd like to thank for UKCCS research community to give me this opportunity to present some of the funding of the grant which was awarded in 2022 and in this series, this UKCCS web series, the Project Showcase. Title of my presentation is exactly title of my, the funding was Project Evaluation of Properties of Biomass Wood Pellet in Power Generation Sectors. And so this is the contents of my talk. It's just a bit introduction. We look at drugs as maybe the first and international example of the power plant which use a biomass, and we look at what is the UK strategy in using biomass, aim and objective of this project, and what has been done in this project, what's the flowchart of the project, and some result discussion, conclusion, some impact which made it, and acknowledgement, and last not least, I'm very open to receive any constructive feedback to move on this project further. So all of us now, this community is well known that we are at energy transition and we would like to use any kind of the source of the energy, including trees and all the foods. Of course, the plan is not just to defrost, but use the trees which fallen and all the crops, all these that is waste, converted to pellet, and then produce some electricity. And of course, there is a CO2, which I show you is much less CO2 than fossil fuel. So then is measuring, and then of course, then finally capture it and store it. So this, the first figure shows that renewable energy, if you like to achieve 2015, target net zero, we have to increase our portion of using the renewable energy, and from say 2015, which was 14% to 63% in 2015. So the second figure here is provides a breakdown of renewable deployment, and you can see the share of the power sector is 58%, and consider that all we can see in the street. The motorway, just you see the electrical vehicle, etc. So, and also pump heating, this is including that is going to be, the key role of bioenergy is 32%, including district heating. Human beings use wood, I can say thousands, million years, but now we're going to use wood to produce electricity. That's the change from warming ourselves to survive now is to produce electricity. So in UK website, you can see that in spite of so many criticism on using the wood, so government legally approved the use of wood pellets to decarbonize the economy and reduce greenhouse gas emissions. Job creation, employment, social, economical impact has been seen by development of the supply chain of producing wood pellets. Biomass heat is expensive. It's 23% more expensive than heating from the gas boiler. But however, UK government subsidized, and this has become 52% cheaper. Using the waste wood and energy crops available in the UK, we can meet 5% of the national heat demand and save 5.3 megatons of CO2 equivalent per year, or 1.5% of the UK emissions. If you'd like to know more, you just follow the link to UK government website. So Drax is, I know I met the CEO of Drax, there's a whole thing is so many. I think 2017 came to University of Bradford, had a presentation, maybe the first lady, woman in engineering, and sitting in the CEO chair. The challenge that time was, how to do with this fossil plants. And she went through so many stories and challenges, and finally the decision was to use co-firing of the wood pellets and coal. To my best knowledge, is 4 out of 6 of this combustion chamber has been changed, and 300,000 tons of the on-site biomass storage. This is what you see. This is dome. This is the storage of the wood pellets is under this and is in nitrogen blanketing. And the reason that we use nitrogen blanketing like that we use for the oil industry, gas industry, just as a nitrogen as a neutral to prevent fire and the explosion. So in UK, that then biomass in the strategy has been seen for electricity productions, and then for BECCS, biomass energy with carbon storage, has been seen as a strategy can play an important role in providing dispatchable power. Used for heating, of course, and in other industries also, this government aims to facilitate industry switch from fossil fuel to low carbon using biomass. So this project, although is small, but I'm very pleased with the outcome, with the activities. So that's the aim of the project. We like to look at the chemical and physical properties of the wood pellets at a single particle level and hopefully link it to the bulk material by characterization of the wood pellet and then rate of energy release and gas emissions such as CO2, other greenhouse, and hopefully find a potential correlation between liberated energy and emissions. This is the chart which shows that even we put 5 samples at our proposal, we gone to 12 samples and look at the size, density, durability, strength, density, moisture, all these kind of the characterization of physical and mechanical properties, and as a minimum of 150 tests done for these 12 samples. So this is flow chart. We received the sample from different sources, power sectors and supplier as well. We just measure size density. This wood pellet has to be milled to be able to combust and put in the combustion chamber. And then, of course, once we're milling, then sieve it. So we did a chemical analysis. These are the universal method used in the literature, using the academy, TGA, EDX, SEM, heating value, CO2 emission, and mechanical and physical properties, size, distribution, structure, strength, and density. And with my background on the particle technology, one of my backgrounds, so I found this project, is good to move on, and then I did for this. So once we mill the product, so different samples, you can see most of the particle is less than 1,000 micron, which is suitable for put in the combustion chamber, and the sample C has a more uniform distribution. If the particle is big, so that's on desired size and has to be again back to recycle to the process for milling. This is a SEM test. There's 6 samples. There is no uniform structure. It's showing the mix and heterogeneous morphology. For 6 samples, we measure carbon, hydrogen, the sulfur and oxygen. That was one of the expensive tests we did for all the samples. And you can see, for example, that carbon content is 48 to 50%. And I think the Rax is right that they have reduced 50%. If you are a chemical engineer, if you assume that this reaction goes stoichiometry, so you have 50% carbon less than coal. So that is definitely is just a rule of thumb. You have 50% CO2 less. There is sulfur, which much more sulfur in coal, but in wood low. If sulfur burn, all of us we know that it's gonna produce the sulfur dioxide, which can go with acid rain. And in 1970, when the drought was there, so the people, the northwest, the wind here in UK, and the people complaining that acid rain, etc., in the other part of the UK. And for your information, we are just, I'm talking from less than 100 miles from the drought station. So, but there is this sulfurization. What I am thinking that chemical engineer, they challenge and they find the solution for sulfur. Carbon dioxide is much easier than sulfur and is less hazardous. That's what I'm optimistic on DECCS. We're using TGA, so all of you know that is just heating the sample, the first drop. You can see that is the moisture removal. And that's the ash which left, and then the rest is the volatile matter, some aromatic, etc., which evaporated. But again, that's one of the challenges, either coal-fired plant or biomass fired plant, is what to do with the ash. And I know that there is one more project funded by UK CCSRC to deal and tackle this kind of the ash, which is out of the scope of this talk, but just for your information. So this is the milling, is an energy-intensive process. That's a lab scale we put in the rotary ball mill, and then after that, we measure, durability simply is the mass after and before crushing. You can see as compared to industrial scale, this is our lab scale. And one of the challenge again here is milling is energy-intensive process. And you can see here that, mechanical durability is very good, then it means that you have 0.5% dust. If it falls, it's still high, but you can see between 0.5 to maybe 0.1%. Dust formation during handling, storage, transportation, which is issue, you cannot do that. And also you can see another property, you measure the strength of the particles. After milling, again, that's a compaction. As a material engineer, this is a famous machine instrument. You use it, you break the material, you measure crushing force, and then you can see maximum force and density. So you can see that is the characterized density of the particle, at the single particle level. And that's important property if someone going to, buy and order these properties. Otherwise, you will face with the dust formations. We look at the moisture and relation with the bulk density. Bulk density is translated to cost simply because you can imagine thousands of tons of this material receiving a power plant. So the lower bulk density you have, so then it means is your cost high. And then the transportation is by volume and mass. Yeah, so this is where the shipping industry charge the company. So this is very important to understand which kind of the material you would like to have. So that is the bulk density is from 590 to 630. The main thing, the objective was to look at CO2. So we look at the carbon content, and also we measure CO2. CO2 is in the range of the flue gas, and I think that's not off. We have the the power plant produce 10 to 12% flue gas CO2, which is here. You can see for different samples. Again, we have seen that. So we use bomb calorimetry. This is a laboratory scale in our limited laboratory, which I set up by using this fund and the other funds. So using measure the heating value, and this is correlation of the carbon content and the heating value, which is a slightly positive correlation. Looking the wood pellets, without looking the moisture is not complete task. So we look at the moisture, and you see that heating value is changing with the moisture. This is due to substantial energy which is required to evaporate moisture during combustion and ultimately diminishing the overall heating value of the pellets. We also try to understand relation of CO2 and the moisture, and you can see this is a decreasing trend indicating that increasing moisture content reduces CO2 emission, and higher moisture content corresponds to more oxygen and hydrogen and less carbon, resulting in lower CO2 emissions. So for a couple of samples, that 4 samples which I have shown here, you can see the trend, heating value reduced by increasing moisture, CO2 at the same time, but there is looks like optimum 7 to 8% moisture content. That is, we found this is, for most samples, this is like optimum. This is, still we are working on it, but we found this is a good one that you have 7 to 8%. We look at heating value, again, trend with CO2, you can see that the size of the particle, if you have very low particle size, that you will have the dust formation is another issue, but the surface area is increasing. That's a trade-off between dust formation and the heating value. So the 500 micron looks like is a good one. Then you have less minimum CO2, because once you're increasing, the CO2 is increasing and it's giving you the heating value. So to understand what really happens, we need to look at the internal structure of the pellets. So for this is a recent data we're using the nitrogen absorption technique just to find the porosity per size. And this is ongoing. According to IUPAC classification, our sample is showing type 2, which is non-porous or microporous characteristic. The better result is showing with increase in humidity, the surface area of the sample also decreases. To conclude the characterization of wood pellets, there is a complex interplay of factors that influence CO2 emissions. Once at the beginning is just simply looking now is wood with combustion is simple, is not so many factors, physical and chemical properties impact. Notably, moisture content play a pivotal role affecting aspects such as pellet durability and heating value. We did all possible characterization with our, again, limited resources at the university, from density to moisture content, durability, heating value, carbon content, TGA, all these. And we found that this finding underscored the multi-phase nature of the wood pellet in production and pelletization and utilization. For your information, this is an ongoing project. We are trying to better understand the influence of physical, mechanical, and chemical properties on CO2 reduction, and finally find the optimum wood pellet quality, which we can recommend to industry to order it. So outcome of the project after this finish, because now is 2024, we were, based on the success of the first, we found another source, another 10K is a publication, and a couple of the students have been graduated. One of them is in here, and in this meeting, still working as a student. The future work is in to optimize the pellet parameters, just to see how we can find the best pellet, in terms of the CO2 emissions and the heating value. Other type of biomass, we are looking for, because especially in UK government, based on the UK strategy, biomass, perennial biomass has been, mentioned. We are working through that because of abundance of this kind of biomass. In UK, we are trying to model and study integrated system of biomass with CCS. And of course, life cycle assessment. This is a very, very challenging, and so many criticism, especially in media, is on this kind of the power plant. So I'm representative of my group. which I thank them. Dr. Sunny is in here in this meeting, is the lecturer. It's Charlie Scott. Now she's doing PhD. I'm happy that she's inspired some way to start and further study going different level. Manish graduate actually is in ongoing MSc student, and a couple of the other students. And last not least, sponsor of the project, Custom is industrial sponsor, and EPSRC, and of course UKCCS, which gives me the opportunity to present this work and also for funding. You can see this is where Drax was it. Thinking back to less than 10 years ago, that's how every day was in the news, the people trying to shut down the plant, and you can see the hill of all these ash, which is from the combustible coal. Now, I don't know if you have opportunity to go, there is a different environment around, there is a hydroponic farm, and you can see a Skylark Center. This is a park which is now trying to somehow embed the circular economy and sustainability also to please, in terms of the corporate social responsibility to please the people in the community. And last but not least, I'd like to thank Drax. This was a research project, which this was not funded by them, by the way. But what the support they give, also they're giving me opportunity to, especially for my student, because I'm looking at the master project here, to take a student to the heart of the plant, which many industries, they don't do that because of safety, etc., etc. But we were, we thank them as well, and we can see a couple of the photos that taken to go to the combustion chamber where the coal is, where the wood is milled, and then put in the plant. Yeah. And also thank you for your attention and listening. Thanks for giving your time. Thank you very much. I'm happy to answer any question if there is.
Thank you so much for that, Nejat. It was an absolutely fantastic presentation. I've got hundreds of questions myself, but if you have any questions from the audience, can you please pop it in the chat or raise your hand? We've already got one here. Your name, so Herbod, if you'd like to ask your question.
Thank you so much for interesting presentation, the outcome of the biomass and particle. Just have one question. Is there any limitation to minimizing the size of the particle? As you can see in the graph, when we reduce the size of the particle, you have a higher heating value. I just want, that's interesting. Is there any limitation to the reducing the particle size?
Yes, of course. You know that once the particle size reduces, surface area is increasing, is a good news for heat and mass transfer, but it's a bad news for handling, because then the cohesion force is increased between particles. Then even with little moisture, you can have agglomerations, and then that has a knock-on effect, has a negative news for going to the boiler. So we need the optimum particle size. For pharmaceutical industry is a totally different topic. Again, for that, I'm working in particle technology. Yes, surprisingly to me, we had 500 to 600 micron. This is our lovely particle. I come to 500 here, looks like something, but this is a totally different. It's energy sector. That's a pharma sector. I'm trying to understand. It's a very good point. Thank you.
Thank you. It's interesting because even it would be next project to the life cycle to see that the energy consumption of reducing the particle, it would be a challenge. That
yes, you are right. Totally right.
Thank you so much. It's very
interesting. You're welcome.
Perfect. Thank you so much for that question. We've got one in the chat from Kofo. They were just wondering, how did you test the sort of mechanical stability of the biomass used in Drax?
We're using two tests. We use the milling, the rotary mill. We use the durability, and I'll show the equation here. And the second time, we're using the compression strength. So two tests we did. So we just put in the rotary mill, maybe a couple of minutes. It just wants this break. Then we see that how much is the attrition of the particle as compared to the mother particle original. And then we just plot it here. It's not difficult, but there are different tests, I agree. So someone may say they use impact test. You can impact the particle to the wall, different speed, and then measure it. But yeah, so it depends, you know. But because they use mean, we say impact is not gonna be good kind. We try to have similar kind of the process is in the plan and what we have in our lab. Yeah. I hope I answered your question correctly.
No, that's great. I'll just ask one myself then. You said that you're kind of looking into the sort of optimal pellet. Do you think that optimal pellet is currently available on the market? How far off do you think we are from
No. There is no. I think this is what industry loves to find out. Because there are many sources you can imagine, you know, so from Europe coming here, Canada, you know, UK, Scotland, you know. Yeah, they're trying to find. Yeah, there is nothing. Yeah, that's what we are planning to find. What gonna be optimum in terms of the properties and which fit to the end user, which is our big powerful.
No, yeah, that's fantastic. Thank you. It's fascinating the sort of diversity of available pellet compositions around the world and how many countries will feed in. It's really practical research. Just okay. I think we're going to have to move on to each presenter had 25 minutes. I think your time has come up, so we're just now going to move on to our next excellent presentation from Ali from the University of Edinburgh, looking into the sort of carbonation of negative emission technologies. Thank you very much for presenting. And just as a reminder, both of these projects were funded by the UK CCSRC Flexible Fund 2022. And we're just presenting them to you here for the showcase.
Hello, everyone. This is Ali from University of Edinburgh. I'm a Chancellor's Fellow in Net Zero Technologies, and I have a few projects on different aspects of it, from hydrogen generation storage to CO2 capture and storage. So this presentation is the results of our flexible funding project supported by UK CCSRC, and two students also worked on this project and learned a lot during their dissertation. Just before going to the result, I just want to say why we did this work. As you know, UK have ambitious goals of reaching net zero. What does it mean? It means per each kilogram of CO2 that we emit to atmosphere, we capture another kilogram. So in total, the amount of CO2 we release to atmosphere equals to zero. But the amount of CO2 we emit depends on few parameters. First is the population, which is rising. Then service per person. The service means like the car we use, the vacations we have, the house heating, and literally the food we eat, everything related to humans. And the service per person is also increasing because the life quality generally in the world is increasing. But energy per service is also related to energy per service, means that, for example, the energy required to prepare all of these services. But it is reducing because we are having more efficient cars, better insulations in the buildings. And lastly, we also have the CO2 emitted per energy unit we produce. This is also reducing, but it won't get to zero in lots of industries. That's why we need to have some negative emission technologies to cover those industries that will generate more CO2 and won't be easy to replace. Here is just a figure from IPCC 2022 report. Here you can see a few scenarios of how we acting as global warming. If we want to limit below 1.5 or let it go a little bit higher and return it back to less than 1.5 or limit to 2 degrees of global warming. And you see in all scenarios, we will still have lots of CO2 emission, especially from in the heavy industries and some industries that will still need CO2 emission. And you can see in these lines, there are some models that are showing how if we want to achieve this net zero goals, we need to have some CO2 capture units. And if just this orange in the bottom shows current policy that we don't have any carbon capture, but even if in moderate acts against the global warming, we will need to have 1 million tons of CO2 captured and stored from air. So in this research, we had a very simple objective, but it worked very surprisingly well. So we get the CO2 and we also get sodium hydroxide. We have a reactor. We inject CO2 with different solutions of sodium hydroxide. Then we let it react, and it forms bicarbonates and sodium hydrogen carbonates that's used in chemical industries. It has been used as an activating agent in paper and food industry. So we get the CO2, we get some chemicals, and we turn CO2 into value-added byproducts. Here is just how it works. We initially need to produce this sodium hydroxide. It can be produced from sodium chloride with electrolysis. If we use renewable energy, we can close the circle to have fully green circle. Sodium hydroxide also could be coming from other sources. For example, it is one of the petroleum byproducts, or it is like a waste in some of the industries. Then we get CO2 from flue gas. Because the percentage of CO2 in the flue gas is high enough to quickly react. Then we can use any 3 types of the reactors. I will later on explain what are the differences between these different types of reactors. Then it creates sodium carbonate that can be used as an activating agent that it could be used in construction materials. It could also be used as a soap and detergent in pulp, paper industry, glass industry, and many other industry. Even in some of the food you get, you can see the name of these products. But it depends on how the quality of the method we use, that if it is food quality or not. And with this, as you can see, I put like a few red lines. It can also in certain parts can be used instead of Portland cement just as an additive. It reduces the amount of CO2, and it also can for sodium carbonates that could be coming from lots of energy consuming products. It could be coming from a cycle that is totally carbon free. In terms of reactors, there are mainly 3 types of reactors that are used. One is spray towers, in which the chemicals is sprayed in a reactor in the air, and it gets in contact with CO2. It's good that it has very fine droplets, so it reacts with CO2. But the problem is that because the water is getting evaporized, because it becomes very small droplets, we have a big water loss there. There's also packed towers, which there are different packing materials that are used, and it's covered with the solution. Then gas is flowing through those materials. But the problem with these is it has lots of capital cost, and because we use sodium hydroxide, it has a high pH, and material gets degraded over time. But the other one is the bubble column, which is simply a column. We put the solution in and inject CO2 from bottom. It reacts with CO2 as CO2 flows to the column. So within this one, the main problem is the less contact area between phases, but it is very simple, cheap, and easy to scale up. That's why we used this type of reactor in our experiments. we tried different types of glass and different types of reactor, because this experiment, the reaction when we used pure CO2 to inject through sodium hydroxide solutions, because the reaction was so quick, using different we tried many different reactors, but the complex reactor had complexities removing the materials, or like how much liquid we put each time, how we should handle. But the simple, just the simple one worked better than even the complex one. So we have a simple glass tube. We have a accurate, precise balance. We have a CO2 bottle, research grade CO2 bottle. Then we have a flow meter and a nozzle here. Then we inject the CO2 from bottom, because this is the reaction is so quick and it could come out. We don't filter the top, just 10% of the glass is filled with sodium hydroxide solution. And after we finish the experiment, take this out, weigh the sample during the experiment, and then take the byproducts to different analysis such as XRD and colorimetry. This is a better like a description of methodology. We start bubbling the CO2, then we get samples of slurry, we do pH reading, we at the end we also did Frixie modeling. Then after finishing the experiment, we dry the samples and we use XRD and colorimetry to get inorganic carbon content. This is the list of experiments we did with different concentration of sodium hydroxide, and also we did at different time, each one at different time scales. For each of these experiments, we set totally new experiments. So it was not continuous. For example, if we wanted to do 8-hour one, we had to set from beginning, because we didn't want to take sample during the experiments. Otherwise, our end result would have some problems, because we wouldn't have the closed system. We also did the same experiments with potassium hydroxide, but in my today's presentation, I just put the results from sodium hydroxide, because the time was limited and the results exactly was the same. I put some visual, just some photos of it, and as you can see, even though we just fill a little bit, it immediately reacts, and at the end it turns into these solid white byproducts that we use in many industries. And here just some of our results. As you can see, for different solutions, as you can see, with time, our pH goes down, because CO2 reacts with sodium hydroxide, and also that removes some of the OH ions, and it reduces our pH. But you can see in 12.5% sodium hydroxide, it even came to lower pH. But this is not because it is better, but it's because in 50% usually the reaction is so quick, and after this point we didn't have much liquid to be able to get the pH. And the next part was, after we get these white solid particles, we do XRD and colorimetry on them to find out the amount of inorganic carbon content versus time. And as you can see, usually it reaches something between 10 to 14%, but when we had like high sodium hydroxide percentage in few points, you can see even we came to lower than 10%. It was mainly because the reaction was so quick that generated heat and removed the water so quickly that I think probably engaged some of the initial sodium hydroxide content in it. But as we go further along and flow more CO2, those unreacted sodium hydroxides still react. And you can see even with two different methods, it gets to the same number. And these numbers are very, they are very close to the numbers we get from Frixie modeling. So we get a very nice stoichiometric values when we do this reaction. So this is a very simple reaction that we just flow the CO2 and reaction goes as expected and captures the CO2 efficiently. Here, just some summary of the results. Then within this experiments, we had like two, as you can see, two sections that CO2 uptake rate changed. Initially, the rate of the CO2 uptake was in a certain amount, and it changed after a certain point, and this was quite like repetitive in with different solutions, different repeats. We had two different rates, and literature they said because in this reaction you can form both sodium carbonates and sodium hydrogen carbonates. That is like this difference rate because of forming two different materials. But I remember when we were doing the XRD, there are some other bicarbonates are also getting formed. But as you can see, the amount of CO2 per liter is like very just depends on the amount of the sodium hydroxide. As you can see, when we doubled amount of the sodium hydroxide from 12.5 to 25%, the uptake increased from 0.74 to 1.58. It slightly goes up, but it is also within the range of experimental error we do. So higher amount of sodium hydroxide we have a higher reaction rate, but generally we get certain amount of CO2 captured per certain amount of sodium hydroxide we put in the system. So we had some limitations. We did all the experiments with this to be able to have the same results and repeatable results. We did the flow rate on a certain constant flow rate. So the next step is to try to do in other flow rates. The bubble dynamics can be changed. For example, the technologies for nano bubbles. Now we have those technologies that we can use nano bubbles to increase the surface. We didn't do that in this experiment. Here we did our steps of sodium hydroxide was 12.5, 25, and 50. We can go with the finer steps like 5%, 10%, 15%, 20%. And in all these experiments, we used 100% CO2. So we had high CO2 purity, which doesn't exist in nature, and it's like as a pure. So if you want to do, for example, in coal-fired or gas-fired power plants, we won't have pure CO2, and it will be between 3 to 70%. And also we used PhDs. We did some extra analysis like pH, thermal conductivity, and we did some XRD and colorimetry, but we can do some TGA and like also have some in situ measurement such as Raman spectroscopy in the future. But this was very early stage, and this flexible funding gave us the opportunity to get some initial results. But the key findings was that if CO2 can be efficiently get stored in sodium hydroxide, and it could be generated in different methods, even from excess electricity. The reaction rate was so rapid, and when it gets in contact, it reacts. The capacity of carbon storage is like same as the like theoretical capacity, so we achieve close to maximum theoretical CO2 capacity. Also, the result shows that this could help for environmental impact, but we should keep in mind that the sodium carbonates have very limited use. So, for example, in the UK, we need 50,000 tons of that. So it won't be a million scale ton in each country, but in some globally it could be in a few million tons, but it won't be in a scale that can capture all the CO2 just with this method. Then we will have lots of excess sodium carbonates, but it would be enough for them to take part in CO2 capture technologies. This is very scalable, and as you can see, even different concentration with different scenarios, we came to same storage capacity, and the purity of the carbonates formed is also important. We also need for the, as I mentioned, there were some limitations, and for upscaling it and understanding these different carbonates we form, how we can manipulate the system to get into certain types of carbonates efficiently. This was end of my presentation. Please, if you have any questions.
Perfect. Thank you so much for that, Ali. That absolutely fascinating presentation there. If anybody's got any questions, please pop them in the chat or raise your hand. We'll give you a couple seconds to pop them in. Oh, we've got a hand up from Hirbod. Oh, lovely. Go for it.
Yeah, thank you for presentation. I just have one question about the flow rate of the bubble of carbon dioxide. Do you think that this flow rate affects the total efficiency of the
Sorry, I cut.
catching carbon dioxide, especially in larger scale? Imagine you want to have a higher flow rate, and maybe inside the box. Hello, do you hear me?
I'm not sure if I got your question correctly, but I think you're mentioning about flow rate, and maybe if I just tell about that. So the flow rate we had actually was like the minimum we could get from because it was hard to handle it. So we should have gone for a highest or lowest to be able to have a constant. So we went to the minimum flow rate. I think 1 cc per minute. I'm not sure exact number, but I can share later on if you send an email. But in a higher flow rates, the reaction is faster. So this reaction is really like the reaction just immediately when CO2 gets in contact, it reacts. So if you have a higher and if they're in contact, it reacts. So this is a very favorable reaction that CO2 once in contact with sodium hydroxide, they immediately react.
Thank you.
So if you have a higher flow rate, you'll be high. But when as you can see, I mentioned we used only 10% of that column. When you had a higher, it would come out. Some of the whiter stuff would come out, and we wouldn't be able to measure it. So we needed
maybe exactly. This is maybe there is a flow rate and the distance high of the column, or using some other technology to mixing to have a better mixing with the flow to absorb the carbon dioxide. Well, it's very interesting that's using the we can do in the. I will contact you for the question.
Yeah, definitely.
Thank you.
Great. Thank you so much for that great question. Really insightful. I'll just ask one myself. This is absolutely fascinating to me, a whole new space. How your choice of reactors, do you think it would change the sort of bubble dynamics if you were to swap to a different one?
So if we had changed a different one, I think the results wouldn't change much. But the bubble dynamics, for example, the higher flow rate we have means more energy we consume. So we have two options to increase the flow if we want it to even happen faster. The rate it happens when we have pure CO2, it will happen fast enough. But because we will have less amount of CO2 in the air we want to capture from flue gas, then we have two options to increase the flow rate or lower the bubble amount. So, for example, using this water stones that they put in like aquariums, the stones that they put in aquariums for the airflow. I mean, using that increases it like, but it's because we even tried those, but it gets blocked so quick because it's so that we thought it is bigger. But yeah, in the future we are thinking to see how we can change it to have a very low flow rate and low energy consumption and very low construction cost. So it would be very cheap to apply this technology.
That sounds absolutely fantastic, and it's so scalable as well. That I think that's the way forward.
Yeah, it's just like you can just build as like the column as big as you want, and put as much as you want, and it just like immediately when. But the only limiting thing is we have limited use for the products, unless if we can kind of find a way to increase their purity in the construction materials, and yeah.
That sounds like another research project there. It's I think we are coming towards the end of the time here. So I just want to say thank you both to Nejat and yourself, Ali, for the two fantastic presentations here.